So I'm happy to present Misha Kornev, who will tell us about weighted colimits, Gambino's theorem, and Reedy model structures.
Okay, thank you. Now I would like to talk about weighted colimits in unreached case, first of all, and we have a plan for today. The first point is weighted colimits in unreached case. The next point is enriched weighted colimits. The third one is weighted colimits as left Quillen functors. And the last point, I think we will start to talk about Reedy model structure. Reedy model structures. Okay. Now I'll give the definition of weighted colimits. If we are given two functors f and w, between sorry, it's enriched case. It's enriched case, but first of all, I'd like to start with the unreached one. If I have a functor f and the other functor is so-called weight w, it's a set valued functor. This is a weight. Then we can define the object, the colimit of f weighted by w. This one is defined by isomorphism. Maps between these objects, this object and M is an object of the category M. Is this set is isomorphic to the natural transformations between the functor W and this functor. Okay, but FM is co-complete. Then we can use the AND notation if M is complete. Then we'll have that the latter term is the same as by Ninja unit dilemma is the same as end of this set of this by functor. Okay, but we can use a definition. Sorry, we can use the fact that this guy can be moved in this this site, and we can write that this is a saying that cotensor product tensor product of WC and FC, and it maps to M. Okay, but now we can move the this integral and we will have sorry, we have this of course F M, and now it means that we have this expression. But of course, we have that this weighted colimit is just a quotient. So we can take this isomorphism as a definition of weighted colimit in unenriched setting. Okay. Let me give an example. The first simple example, when we take the constant weight, constant on the terminal object, then we have this one, but it is this is a muted quotient, and hence it is just a colimit, usual colimit. Okay. The next example. We can take the following weight. It's just a representable functor, and we can use the ninja unit lemma or co-unit lemma, and thus we have that this weighted colimit is just is isomorphic to the functor f. So okay, now also we can describe the left Kahn extension or right Kahn extension by means of the weighted colimits and limits. For example, left Kahn extension of the functor f along k, if we have the following diagram, f maps C to M and K from C to D. Then we can write this left Kahn extension as a quotient. And hence it is just a weighted colimit, and with the weight looks like this one. Okay. So and now and now we have a natural transformation between the weight and the constant functor, and this natural transformation induces the map between the colimit with weighted colimit is a functorial, and thus we have the induced map, and we have a contravariance in the first on the weight. Thus, we have the following map from this weighted colimit, which is usual colimit, and weighted colimit maps to the usual one, usual colimit, and this is a so-called comparison map. Okay, but also we can describe the weighted colimit as a co-equalizer, because we know that coent is just co-equalizer, hence we can write this expression. Okay, and the last example in this section, usual homotopy colimit of the functor f is weighted sorry, is I think I'll say I'll talk about later. Okay, and now I would like to talk about weighted colimits in enriched case. Weighted. Suppose we are given two functors between V enriched categories, D and N. Suppose say the weight W between these categories. These are some V functors. Okay, then the weighted colimit is an object of category M, such that we have the following isomorphism. It looks like a definition in an unenriched case, but here we'll have some problems with the coherent definition. We should introduce a new notion for enriched, so-called enriched coherents. Okay, and now consider the following example. Consider this trivial category, which consists of the one object and one morphism. And of course, we suppose that V is a monoidal, symmetric monoidal category, perhaps model category. V is a monoidal category. And this one is a unit in this category. And we have a V functor from this trivial category to some V enriched category M. And this functor is just an object of M. Object of the category M. So we can identify the V category of functors with this category. And if we have a morphism from this category to M, and suppose we have this map, then by definition of weighted colimit, we say that this is a weight. So by definition of weighted limit, we have the following isomorphism. So this weighted limit is just a cotensor product between V and M. Okay, and in the same way, we can conclude that the colimit with the same way of M is just a tensor product. Okay. And now I would like to talk about the definition by coherent and so and in I would like to give two definitions. The first one is and in enriched case, and the second is and in enriched case. in enriched case. So in an enriched case, we know that covariance is defined by means of the following isomorphism. That if we integrate this by factor, we will obtain the natural transformations, or it is the same as a equalizer. Okay, and in enriched case, we should replace this term by the copower by the power term. We should replace this term by this one. Which of course is the same in the unreached case, we know. Okay, so the definition is the following. Okay, and of course, in enriched case, we have also the V-unit dilemma as in an unenriched case. Lemma theorem. V-unit lemma. For the factor f between the categories, and for any object d, we have the following isomorphism. This lemma can be derived from the definitions, so of course. Okay, and I'll give example. Enriched the categories V. If I have the situation when both weight and our factor are V-valued, then in this case we have that this weighted limit is just a class of natural transformations, V natural transformations between the weight and the functor f. Of course, we suppose that V is a closed model category. Then we have the following isomorphism from definitions of enrichment, and this is a unit in the model category V. And then we can use the isomorphism from definition of the weighted limit, and thus so this limit is the object of V natural transformations from the weight to the our functor. Okay, to our functor. From this example, we can conclude that the maps between object from the category M and weighted co-limit is the same as this one. We know that this weight is a factor between D, some category D, and V, but we know also that morphisms in the category M are just objects in the category V. So it defines a functor between V enriched category D and V enriched category V. So we are in the setting of the previous example, and so it's just the following weighted limits. Weighted limit. Okay, and now I'll formulate and prove the following theorem. Which tells that the weighted co-limit and the enriched coens are the same, but the proof is the same. So yeah, the proof is the same. So I think I'll need this one, but I formulate it when M is tensor and cotensor. F is following V functor, weight. Then weighted colimit, as in enriched case, is just a weighted. It's just a tensor product, and the limit is a co-tensor product, and they're defined via coend and n respectively. Whenever the weighted limits and colimits exist, of course. Okay. Now I'd like to talk about weighted colimits as a left equivalent bifunctor. Weighted colimits as a left equivalent bifunctors. Now I want to give the following theorem. This is a Gambino's theorem. Let M be a simplicial model category. Suppose that the category of weights is the category from diop to simplicial sets is occupied, is equipped with the injective model structure. We call that injective model structure when we have pointwise weak equivalences, and also we have pointwise cofibrations, but fibrations are defined by means of lifting property. Okay, and the category of diagrams which is equipped with the projective model structure. It is a dual notion. Then the functor tensor product is a left equivalent functor in two variables. Recall that we say that the functor phi between these categories is said to be left Quillen by functor into variables. If the following conditions hold, the first one is that this functor is co-continuous in each variable. The second one is that if f is a cofibration and also G is a cofibration, then the tensor product which was defined in the previous talk is a cofibration. But also one is trivial if F or G is so. So, okay, now I'll prove this theorem. Firstly, the following conditions are equivalent. Following conditions are equivalent. The first condition that the functor phi from this category with the objective model structure times to this category with projective model structure to M is left Quillen by functor if and only if the following functor theta with the projective model structure to the following category is a right Quillen by functor, and the last condition that psi is a right Quillen by functor. Okay, but we know that M is a simplicial model category. So we know that the following holds that if F is a psi is defined. Sorry, psi is defined pointwise by cotensor products. And thanks to definitions of simplicial model category structure and thanks to definition of their right Quillen by functor, we are done. Because we know that if we have if we have maps, I'll do the following diagram. If I have an arrow f from the object m1 and to m2 and the following arrow, then we know that we know from definition of simplicial model structure and the definition of a right Quillen bifunctor. It's easier to verify that this is, of course, right Quillen bifunctor by a pointwise inspection. Okay, so we're done. And this theorem gives us two approaches for finding homotopy limits and colimits. We use we use two different model structures, but these different model structures give us the equivalent results. We can change model structures in this tensor product by projective model structure and injective model structure respectively, and the statement of the theorem will be true. Of course, we can take in this term the projective model structure and this some injective model structure. Yeah. And thus we have the following corollary. Let M be a simplicial model category and D be a small model category. If M is a cofibrin generated, then the projective cofibrin replacement defines a left deformation for a colimit functor. So homotopy colimit can be computed at the colimit of any projective cofibrin replacement. The proof is easy. We know that homotopy colimit. We know that usual limit is just as the following tensor product functor. And now we can choose a model structure. these arguments. Suppose that on the first term we have an injective model structure, and on the second we have a projective model structure. So we know that the terminal functor is pointwise injective, of course, because we know that simplicials, each object of simplicial set is cofibrant and okay. And for the second argument, we should find the cofibrant replacement in the projective model structure, or projective cofibrant replacement. Okay, so this proves the theorem. But if we change the model structure, we will obtain the other approach of the computing these homotopy colimits. If we choose on this category projective model structure, then we should find cofibrant projective cofibrant replacement for the constant functor, and it turns out that it's just a Neuer functor. And in the second argument, we will have an injective model structure. So we should just have a pointwise cofibrant diagram. And so for calculation, for computing the homotopic limit in the second approach, we can use just we can use just bar construction. We will obtain just a bar construction. Yeah. Okay. And for finding the projective cofibrant replacement, it turns out that the following fruitful lemma helps us. And what is lemma? The following is lemma. Says that if we have a map between two functors, let this map be any a cofibration in a model category M. Then the induced map it means the pointwise product. For example, this term means that we have a coproduct over the over these arrows over copies of A. Okay, and this induced map is a projective cofibration in this category. Okay, the proof is very easy. We have the following two diagram. We should verify the corresponding lifting property, and this diagram converts into the following diagram by the junction. what is adjunction? We know that this factor is a left adjoint to the evaluation factor by unit lemma. So if we have a Lifton on the, for example, right side, right side, then we have also Lifton here, and vice versa. So we know that this is a trivial fibration, and this is also trivial fibration according to the projective model structure. And okay, this is a obvious one, and I think we are done. So corollary. Any redirect of transitive composite of push-outs of co-products of the maps of the lemma above, is a projective co-fibration. So so consider the following example. Suppose we have the following category consisting of 3 objects and 2 maps. Is a push-out diagram, and suppose that we have a functor from D to M, where M is a cofibrantly generated model category. So here we use a injective projective model structure. And we should construct. We want to find the homotopy colimit of this diagram, and for doing that, we choose the injective projective model structure, so-called, and thus we should construct the projective cofibrant replacement of this diagram, and also suppose that we suppose that this diagram and this functor have the following property, that f a is suppose that f is f a is a cofibrant, f of f and f of g are cofibrations, then we will prove that f is f is projective fibrant. And so for finding the homotopic limit on the following diagram, we just take the co-limit of this diagram. That is homotopic limit of f, just co-limit of the diagram. Okay, so we decompose the map from initial object to the functor f. We decompose it into the three projective cofibrations. I draw the following diagram. Okay. We can form the push out, the following push out. What is the map? This map is just from the junction. What is the junction? We know that this set of maps is isomorphic to the following set. So by unit lemma, this is the same as the following set, but in this set we have, of course, the identity arrow from FA to FA, because we know that this is just a set, and this term is just a coproduct of copies of FA, and so we have of course identity arrow in this set, and by adjunction we can find the arrow U, which corresponds to the identity arrow by this junction isomorphisms. Okay, and then we can form the push out. This arrow, of course, the cofibration, because we have proved the previous lemma, and we know that this map is a cofibration. Okay, so the push out of this cofibration is, of course, a cofibration. And the next rectangle is the following push out. And this arrow corresponds to the following composition. We have that there is an arrow here, and we can compose these arrows. And this arrow corresponds to the identity map, corresponding identity map. And this push out, it turns out, will be the function f. Why it's true? It's an easy fact which follows from that we can see that this diagram is just a diagram from the definition of the coends. We can form the following co-equalizer. But from the co-unit lemma, or you can just prove by universal property of you can verify the universal property of the coend that f is the answer for this co-equalizer. So we now we decomposed this map as the following compositions of cofibrations. So this map is a cofibration, and thus f is a cofiber as a composition of cofibrations. Okay. Okay. The next example. Mapping telescope. Suppose we have the category which consists of the looks like this, and we have the function from this category to the simplicial model category M, and we also want to find the projective cofibrant replacement for this diagram F. And it turns out that this diagram looks like following. We just take the cofibrant pointwise cofibrant replacements, and also we should replace the morphisms by trivial cofibrations. We can do this by induction. The step zero. We just replace the. So suppose that F is a diagram like this. And as a step 0, we just replace x0 by its cofibrant replacement. So suppose Q0 is a cofibrant replacement of the space usual cofibrant replacement. Sorry, for the space x0, and we also define the functor G0 as a tensor product. So as a step 0, we have the natural transformation from the functor J0 to the functor f, and the following diagram. And here we have a weak equivalence, and also it is a cofibration, but the other maps maybe not weak equivalences, so we can fix it. And also these arrows, of course, are the compositions. This arrow we compose with this one. Okay, and the next step. We just consider the following composition. Say that this is a F01 and this is a Q0. Then we consider the composition and we decompose this. Well, we'll take the cofibrant replacement for this map, and thus we have the following diagram. Okay, we decompose this this map into the cofibration followed by trivial vibration. Okay, and then we can form the push out. The horizontal map is obvious one. It corresponds to the identity arrow on the object Q0 from the junction. We have seen this one in the previous example. So, but I can write it again. Just the set with one object, and of course we have here identity arrow. Okay. Now we have the following diagram. So we have here weak equivalence, and of course here, and thus at the end step, in the case of step n, we have we should decompose the composition, the map and thus we will have the following diagram. Okay, so we have the natural transformation between the functor g and the functor f, and g is a colimit of the functors gn. We have constructed the following sequence of the functors. And the colimit of GNs is just, we will write for it, we will denote it as a G. Okay, so we know that the set of a class of cofibrations is closed under the transfinite compositions, and thus we have just constructed the desired projective cofibrant replacements. Okay. And now the other corollary of Gambino theorem that we can take and we can take a nerve as a projective cofibrant replacement for the constant functor that is this functor is a projective cofibrant replacement projective cofibrant replacement for the constant weight functor in homotopy colimit. And also the functor, this functor is injective fibrant replacement for the constant weight in homotopy limit. Okay, proof. We know that consider projective injective model structure. and we only should prove that we have a weak equivalence between. Sorry. We should prove that we have the fact that this functor is cofibrant replacement, but it follows from the construction of this functor by inductive construction. And of course, this functor is a weak equivalent to the point, and f should be pointwise weak equivalence, and thus we apply just the Gambino theorem, and we're done. Should be pointwise cofibrant cofibrant object. Okay. But also we can derive the finality theorem, finality equivalent theorem from the Gambino theorem. We know that homotopic limit of the composition is just this weighted colimit. It's just a corollary of this corollary, and we have a comparison map. So we know that this one is homotopy trivial if we suppose that K is homotopy final function, then this is of course a homotopy trivial, and we know that this functor is projective cofibrant and homotopy trivial also, as there is a terminal object. And so we have a weak equivalence and also we know that by Gambino's theorem, we know that the functor sends trivial cofibrations to trivial cofibrations. As the functor tensor product is a left equivalent function. Trivial cofibrations between cofibrant objects. And thus we are in the settings of Ken-Brown lemma, hence by and Brown's lemma. We have that this map is a weak equivalence. So we have a proof of the homotopy finality theorem. There's a proof. This gives the proof of equivalence homotopy finality theorem from the previous talk. Okay. I think at this point, I want to stop and in the next the next talk will be about Reedy structures and more general more general approaches in studying of homotopy limits and colimits.